Thank you, Stefania. As she said, we'll hear about the Mosel survey and particularly looking at the outflows in the Mosel survey. I hope you can hear me if I stand a little bit here because otherwise you won't be able to see me. No, the microphone? Yeah. Oh, the other side, right. Yeah, now that's okay. Yeah, curse of the short people. Right, let's go. All right, so today's crowd, I won't have to show this picture, but this is the history of our universe. And the epoch that we are really interested in is this epoch of reionization, especially with the JWST coming on in the last 2 years. This is essentially the time at which the universe went from completely neutral to completely ionized or mostly ionized in a span of about 1 billion years. And to understand how this reionization happened, we need to know two things about the galaxy. First, how many of ionizing photons these galaxies were producing, and then the number of ionizing photons that managed to escape from the interstellar medium of the galaxy into the intergalactic medium and went on to ionize the intergalactic medium. Right. JWST is already giving us fantastic measurements about the production efficiency of ionizing radiation, the number of ionizing radiations these early galaxies are producing. But to get the escape fraction, we need to detect the Lyman continuum photons. But the opacity of intergalactic medium, there's so much neutral hydrogen around these redshift greater than 6 galaxy that it's going to be extremely difficult to directly estimate the escape fraction from EOR galaxy. So what's the solution? A solution that we have come up with is looking at galaxies which are not in the EOR, but in a quote and unquote local universe, redshift 3 according to Jordan, and understand their detailed properties and plug them back into our models of how the early universe evolved and see if it matches or not. And to do this, we are doing a Mosel survey, which is multi-object spectroscopic emission line survey. It's particularly looking at redshift 3 to 4, and this epoch is selected because we can get Lyman continuum and the other emission lines, for example, O3 H beta from ground-based spectroscopy. Great. But how do we select EOR analogs? How do we select galaxies which are similar to EOR? What do we know about EOR galaxy? For the past decade, from photometry, we have known that galaxies which are in the epoch of reionization, they have really bright emission line. Most of the flux in these galaxies is coming in this really bright nebular emission line, for example, O3 H beta and 2H alpha. So much so that like 50% of the flux in these emission lines. And this has been confirmed over the past year or so with JWST. Like a lot of galaxies at redshift greater than 6, they have really high O3 equivalent width. For example, 30% of galaxy at redshift 7, they have this extreme emission feature, which is rare at lower redshift. At redshift 0, it's like less than 1%. And then at intermediate redshift, it's about 10% of the galaxy. Okay, so what Ben Forrest particularly he did was he tried to select galaxies using Z4 survey, which had this extreme emission feature. And he found about 100 galaxies at redshift 2.4 and 4 with the high O3 equivalent width. And how these galaxies compare to the JWST galaxy, Ravi Jaswar in the next session, he'll be telling you more in details what they are exactly. What I did was we targeted a subset of these galaxies with the KMO spectrograph on VLT and the Mosfire spectrograph on Keck telescope to confirm whether our photometric selection technique worked or not. And for Mosfire sample, we were targeting a range of galaxy with a range of O3 equivalent width, photometrically selected. But for the KMO sample, which are these golden stars, they were particularly targeting highest for O3 emitters from photometrically selected O3 emitter. And this plot shows the O3 equivalent width versus stellar mass relation for the KMOS and the Mosfire sample, the golden stars and the purple squares. And it essentially shows that indeed the photometric selection technique works. The photometrically selected high O3 emitters, they do have indeed high spectroscopic O3 equivalent width. And in the Mosfire, we were getting a range of O3 equivalent width as the selection technique was for it. Okay, great. So we have this excellent spectroscopic data for this galaxy. What can we do? The thing that I was interested in is, do we see signs of outflows in these galaxies? We are over the past 2 days, we have learned that outflows are really cool and they are really important for galaxy evolution. They regulate star formation, they transport metal out of the interstellar medium. And this is especially important for the early universe because we need to know how metals are transported out of the interstellar medium to understand how the early enrichment of the universe worked. Right. So can we detect outflows in these extreme emission line galaxies? Unfortunately, with single with in unfortunately in individual galaxies, we could not detect significant signs of broad component. But what we did was we tried to stack the sample and see if we see any signature. There were some galaxies which should be black boxes, but they are not there. That's okay. Well, so these are the galaxies that we ended up with. Rest of them were gone from our sample because these were the galaxies which had no sky contamination within 500 kilometers from the O3 line. So essentially, it's a cleaner sample without any sky contamination. And it's a slightly reduced sample, but at least it's clean. Great. So we stacked this sample in a bunch of different bins to try to see if we do see any sign of broad component. Yes, so we do see. So this is one of our stack. The black line is the stacked spectrum for galaxy less than 10 to the power 9 solar masses, and the bottom panel is the residual plot. Here, there should be shaded blue and red regions, but we'll try to imagine that. So this black thing above the dotted line, this is residual after you fit a single component, single Gaussian. Okay, so you can see that there is some residual, and that kind of goes away if you add another component, because the second black line, which was supposed to be red, it's completely fat. It's within the 1 sigma error. So there is a weak secondary broad component. It's relatively weak, but it is statistically significant. All right, and we try to bin our galaxy in different bin: low mass, high mass, high O3 equivalent with, low O3 equivalent with, and we detect this really weak broad component in almost all of our stacks except for galaxies with high O3 equivalent with. Right. Now that we have detected a broad component, what can we learn about this galaxy? Making a lot of assumptions, we can somehow convert the flux in the broad component into a mass loading factor. And this is basically telling you how much of relative amount of gas that is being blown out by these outflow signatures. And this is the, oh, oops, sorry, too fast. Go back. Doesn't matter. All right, so this is the mass loading factor versus star formation rate surface density relation. And typically, the star formation rate surface density, as you move on to high star formation rate surface density, mass loading factor is higher because the galaxy is pushing out more, galaxy has the energy to push out more gas. But for our galaxy, our mass loading factors are similar to what we get in a low stellar mass galaxy. Their star formation rates are 10 times higher than a typical star formation rate of low stellar mass galaxy at similar redshift. But our mass loading factors are not high, as we had guessed. And there was another paper published recently which tried to compare mass loading factor in low stellar mass galaxy. The sample is slightly differently selected, and they were able to detect this broad component in individual sample, and they found a range of mass loading factors in low stellar mass galaxies. And essentially it's saying that the outflows in low stellar mass, high star formation rate galaxies, they are relatively weak. We expected to detect like significant broad component in all of our sample, but we don't. And even after stacking, it's like really weak. Another interesting thing that we found was in one of our stacks, which is the stacks for the low stellar mass sample, less than 10 to the power 9, the broad component is redshifted. The residual here is redshifted relative to the O3 peak. Typically, when you detect outflows, they are blue shifted because the redshift component of the outflow is attenuated. So when so is the redshifted component here, the broad component, does it correspond to the gas inflows? Maybe. In earlier, there have been observations of like really Lyman alpha emitter, and they found like most of the sky, almost 90% of the sky is covered by the Lyman alpha emission. So there's a lot of neutral hydrogen gas around these redshift 3 galaxies. But the gas needs to be photoionized to be detected in O3. And what is the source of photoionization? So I don't know. But it is redshifted component, so it's which is interesting. So this paper was published after a lot of interruption earlier this year, which is good. The work is done, but somewhat. The work is never done. So implications, what are the things that we can learn from this weak broad component? Are the galactic winds suppressed in these really highly star-forming galaxies? Do we need massive galaxies to drive the early enrichment of the universe? Or, as Rebecca's work showed, that maybe we are missing a large amount of outflowing gas. Most of the gas reside in the neutral phase or the really hot phases of the ISM. And maybe sodium deabsorptions, like what she said, is the way to answer some of these questions. And with that, I'll just leave there.